Good morning to one and all. I am Dr. A. Benazir, Assistant Professor, Department of Mathematics, HKRH College. Now, I am going to explain about the topic real analysis in first MSc Mathematics. In this topic, we are going to see the definition of metric space. Now, first we are going to see the definition of what is meant by metric. Let X be a non-empty set. Define D from X cross X to R. Then D is said to be a metric on X if it satisfies the following conditions. First one is non-negativity. D of XY is greater than or equal to 0 for all XY belongs to capital X. Next one, definiteness. D of XY is equal to 0 if and only if X is equal to Y. Then symmetry. D of xy is equal to D of yx. The last one is triangle inequality. D of xy is less than or equal to D of xz plus D of zy for all xy z belongs to capital X. Next definition is metric space. A non-empty set X along with the metric D on X is called metric space. It is denoted by X comma D or simply capital X. For this, considering let X is equal to R, define D from R cross R to R by D of XY is equal to modulus of X minus Y for all XY belongs to R. Now, to verify that D is a metric on R, non-negativity, D of xy is equal to modulus of X minus Y, which is greater than or equal to 0. Definiteness, D of xy is equal to 0 if and only if modulus of X minus Y equal to 0. Then if and only if again X minus Y equal to 0, from this X is equal to Y. Now, the symmetry condition is D of xy is equal to modulus of X minus Y can be written as modulus of minus of Y minus X, that is modulus of Y minus X, D of Y comma X. Now, the last condition is triangle inequality. Now, consider D of xy is equal to modulus of X minus Y, that is equal to modulus of X minus Z plus Z minus Y, just adding and subtracting Z in this term. Now, we can get that modulus X minus Z minus of Y minus Z, that is modulus of X minus Z plus Z minus Y, which must be less than or equal to modulus of X minus Z plus modulus of Z minus Y, which is equal to D of XZ plus D of ZY for all XY Z belongs to R. Now, since D satisfies all the conditions of metric, hence D is a metric on R called usual metric or standard metric. Now, the definition of neighborhood of a point. Let X comma D be a metric space. Let P belongs to X. Then a neighborhood of a point P is a set NR of P defined as NR of P is equal to the set of all X belongs to capital X such that D of XY is less than R. The number R greater than 0 is called radius of N of P over R. Now, the next definition, interior point. Let X comma D be a metric space. Let E is a subset of X. Let P belongs to this capital E. Then P is said to be an interior point of E if there exists a neighborhood NR of P such that NR of P is a subset of E. For example, let X is equal to R and E is equal to Z, the set of all integers, is a subset of R. We know that neighborhood of X is equal to Nx of X is equal to X minus epsilon comma X plus X epsilon. Here, for epsilon is equal to 2, the neighborhood of minus 1 becomes minus 3 comma 1, which is not in Z, which is not a subset of Z. That is, we cannot find any neighborhood of any integer which is contained in Z. Therefore, Z has no interior points. Now, the next example for an interior point, let E is equal to 2, comma 6 is a subset of R. All reals between 2 and 6 are interior points. Now, the next definition of open set. Let X comma D be a metric space. Let E is a subset of X. Then E is said to be an open set if every point of E is an interior point. Example of an open set. Let X is equal to R with usual metric. Let E is equal to open interval minus 1, comma 5. Points of E is equal to all reals between minus 1 and 5. Interior point of E is equal to all reals between minus 1 and 5. Therefore, E is open. Generally, every open interval is open. Let E is equal to open interval 0, comma 5 union 7 is a subset of R. Points of E is equal to all reals between 0 and 5 and 7. Interior points of E is equal to all reals between 0 and 5. Therefore, E is not open. Let E is equal to closed interval 1, comma 5 is a subset of R. Then points of E is equal to 1 and 5 and all reals between 1 and 5. Interior point of E is equal to all reals between 1 and 5. Therefore, E is not open. Now, based on this, the theorem is every neighborhood is an open set. Proof. Let X comma D be a metric space. Let P belongs to X. Let NR of P be an arbitrary neighborhood of P. Here R is greater than 0. To prove NR of P is an open set. That is to prove every point of NR of P is an interior point. Let Q belongs to NR of P. To prove Q is an interior point of NR of P, let taking metric D of P comma Q is equal to H. Here H is greater than 0 and this H is less than smaller. Taking this equation number 1, let N R minus H of Q be a neighborhood of Q. To prove N R minus H of Q is a subset of N R of P. So let we are taking X be an element in N R minus H of Q. Now it is enough to prove that the same X belongs to NR of P. So now X belongs to NR minus H of Q, which implies D of X comma Q is less than R minus H. Saying this equation number 2. Now consider D of X comma P is less than or equal to D of XQ plus D of QP. By triangle inequality, we are writing this. Then which must be less than R minus H plus H, that is equal to R from equations 1 and 2. So now D of XP is less than R, which implies X belongs to the neighborhood of P over R. So therefore, we have NR minus H of Q is a subset of NR of P. That is, there exists a neighborhood of Q which is contained in NR of P. So from this, we conclude that Q is an interior point of NR of P. So now, since Q is arbitrarily chosen, every point of NR of P is an interior point. So NR of P is an open set, and since this is an arbitrary neighborhood, then we conclude that every neighborhood is an open set. Now the next definition is limit point of a set. Let X comma D be a metric space. Let E is a subset of X. Let P belongs to X. Then P is said to be a limit point of E if every neighborhood of P contains at least one point of E other than P. Next definition of derived set. The set of all limit points of E is called the derived set of E and it is denoted by E dash. Example, let E is equal to open at -1 and closed at 10. Limit points of E is equal to -1, 10 and all reals between -1 and 10. Then the derived set E dash is equal to the set of all -1, 10, all reals between -1 and 10. That is equal to closed at -1 and closed at 10. Let E is equal to open interval 1, comma 5 union 5. Limit point of E is equal to 1, 5, all reals between 1 and 5. Now, the next definition of closed set. Let X comma D be a metric space. Let E is a subset of X. Then E is said to be closed set if every limit point of E is a point of E. For this, we are considering the example as E is equal to closed interval 0, comma 1, which is a subset of R. Limit points of E equal to 0, 1, all reals between 0 and 1. So now points of E is equal to 0, 1, all reals between 0 and 1. Therefore, E is closed. Generally, every closed interval is a closed set. Next one, complement of a set. Let X comma D be a metric space. Let E is a subset of X. Then the complement of E is denoted by E complement. And it is defined as E complement is equal to the set of all X belongs to capital X such that X is not belongs to E. That means X is not an element in the set E. For this, we are considering the example. Let R comma D be a metric space. R complement is equal to empty and the empty complement is equal to R. Now, what is the relation between open and closed sets? A set E is open if and only if its complement is closed. Proof. Let E be open. Now to prove is E complement is closed. Let P be a limit point of E complement. It is enough to prove that P belongs to E complement. Since P is a limit point of E complement, every neighborhood of P contains at least one point of E complement other than P. No neighborhood of P is contained in E. So which implies P is not an interior point of E. But what about E? E is open. So which implies P is not belongs to E. So that P must be in E complement. So P belongs to E complement. Since P is arbitrarily chosen, we can say every limit point is a point of E complement. Therefore, E complement is closed. Now we are going to take E complement is closed in the converse part, and we are going to prove is E is open. Let P belongs to E, arbitrarily chosen. Now to prove this P is an interior point of E, since P belongs to E, which implies P is not belongs to E complement. But what about E complement? E complement is closed. So which implies P is not a limit point of E complement. Therefore, there exists a neighborhood N of P which contains no point of E complement. So which implies that there exists a neighborhood N of P such that N intersection E complement is equal to empty. That is, there exists a neighborhood N of P such that N is a subset of E complement. The whole complement becomes E. So which implies there exists a neighborhood N of P such that N is a subset of E. So from this, P is an interior point of E. So since here also P is arbitrarily chosen, so every point of E is an interior point of E. Therefore, E is open. Okay, thank you.